1.3 New functions from old functions. In this section, we're going to review on the transformations of a function. Means we're going to look at vertical and horizontal shifting, vertical and horizontal stretching and shrinking, and, and then reflections. So vertical shifting is basically adding or subtracting to a function value with a constant. Okay? So that way it will go up or down. Horizontal shifting is adding or subtracting to the input values of a function, because input value is on the x-axis, right? So it's going to go left and right. Now, vertical stretching is, or shrinking, is basically multiplying the function value by a non-zero number. Right? If you are multiplying by greater than 0, then it's going to be either shrink or stretch. If you multiply by a negative number, it will include the reflection as well, which is we'll talk about separately down there. So if the constant multiple is greater than 1, then the graph is going to be stretching. And if the constant multiple is between 0 and 1, then it will be vertically shrinking. But however, in a horizontal stretching and shrinking, it's going the other way around. So you're going to be multiplying a constant number that is greater than 1 to the input value, then it's going to shrink. And if a constant value is between 0 and 1, right, and then multiply to the input value, then it will be stretching. The reflection is either you reflect it about the x-axis or y-axis. If you are multiplying a negative number to the function value, that means from positive y value to become a negative y value, so it will be reflect about the x-axis. If you are multiplying to the input value by a negative number, that's basically from positive x to become a negative x, so it will be reflect about the x-axis, y-axis. So that's all about the reflections on this part. So what we want to do is we want to use the given functions, right? The graph of the given functions f, and answer all of these questions part A, B, C. And in this case, what we're going to do is we're going to use a few particular points to do the transformations to make it nice and neat. For example, this point, right? This point, and that point. So this is basically 2, 2, negative 2, negative 2. Right? And for this point will be 1, 3. And for this point will be 3, 3. And this point, last point will be 4, 2. The first question is asking us to graph f of x minus 2. So you are basically talking about the function value minus 2. That's the whole entire graph shift down 2 units. So being said that, my very first problem right here, part A. Now let me write down with this color so that you can see the distinguish. Right? Shift down. So at negative 2, when you shift down 2 units, that will become negative 2, negative 4. 1, 3, you shift down will be 1, 1. 3, 3, shift down will be 3, 1. 4, 2, shift down 2 units will become 4, 0. So now if I connect all of these 2 points, and that gives us the transformations of this graph for part A. So this is my part A. answer. And the next part is your f of x plus 2. So you're adding 2 to the input value, and that will go to opposite directions. So it's going to be shift left 2 units. So you're adding to input value, it's going to shift left 2 units. So that means -2, -2, that point, it will become shifted to the left 2 unit will be -4, -2. Here's the point. And then 1, 3, shift left 2 unit, that will become -1, 3. And 3, 3, shift left 2 unit, that will become 1, 3. And then lastly, 4, 2, shift left 2 units, that will become 4, 2, 2. So this is shifting horizontal shifting, which is shifting left and right. Okay. And this is my answer on part B. Now, we want to answer graph part C and D on another graph. For part C, you can see that -2 times f of x. So it's not only it's going to be stretching, it's also reflect about the x-axis. Okay? Because here's your y value, and you're multiplying by -2 to y value. So first it stretch it, and then what? It will reflect. So you can do it one by one, right? So this will be stretch. Let me change it into pinpoint it a little bit smaller. This will be a vertical stretch because of the y value. And also it will be what? Reflect about y axis. So the very first point, right? So it's basically you are this is your y value. So you're going to be multiplying to y value by what? -2. That's basically what we are looking at. Every y coordinates of the points that we put it right here is going to be multiplied by -2. So it shows you also reflect and stretch. So at -2, -2, right? When you multiply the y coordinate by -2, which is going to become +4. So this point, -2, right? -2, -2 become -2, 4, which is up here. And then the next point, 1, 3. If I multiply the y coordinate by -2, that will become 1, -6. Okay? So it will reflect about the y-axis. So it will be 1, -6 way down here. And then the next point is much easier because it's on the same thing. So it will be 3, -6. And the last point right here, 4, 2. If I multiply the y coordinate by -2, that will become 4, -4, which is going to be right here. So notice that the graph is not only stretching, it's also reflected to what? Not only stretching vertically, it's also reflect about the y-axis. So when I connect all of this point, and that give us the transformations of. So you have a straight edge, so make sure you use that. So this is our part C. Last one. One-third times x, f of 1/3 x plus 1. So you are multiplying by 1/3, which is between 0 and 1, to the input value. So it will be stretching horizontally, right? And then it's going to be what? add 1 to your entire y value, so it will be shift up 1 unit. So stretching horizontally is important to know how to find that out. I want you to, at this level, I want you to think about mentally, but if not, then you will be able to use algebraically. Right? Our original x value on this point, the very left end point, is x is -2. Now, this x value is what? Equivalent of 1/3 x. So the question is, which x value that I need to use so that it will be equivalent to -2? So that's algebraically thinking. So you're thinking about 1/3 x is equal to -2, and that will help you to get the new stretch location, which is multiply both sides by 3 will be -6. So my order pair now will be -6, -2, because we want the same y value, not changing anything yet on the function, right? But however, at the end, what we need to do is what? We need to shift up 1 unit after stretching horizontally. So therefore, instead of -2, -2, now we're gonna what? Not only stretching, it's also shift up 1 unit. So I need to what? Add 1 to my y value. So that will be -6, -1 is a new location. Similarly, I can continue the rest of it. So 1, 3, first horizontally stretching. So 1/3, right? X. Only if your x value is 3, then 1/3 times 3 will be 1. That will give me original x value. So that will give us what? The same y value. Okay? So same process, 1/3 x is equal to 1. So therefore x is equal to what? 3. So we will get when x is 3, my y value will be 3. That is after stretching. But I need to add 1 to my y coordinate to shift up. So it will become what? This second point from the left, instead of 1, 3, now it'll become 3, 4. And the next point, original x coordinate is 3. So now I want to find out the new x value. 1/3 x is equal to 3. So my x is equal to 9. So that tells us 9, 3 is my third point after stretching it horizontally. And then added 1 to my what? Y coordinate, because the whole graph is going to shift up 1 unit. So it will become 9, 4 is the graph. So this is the first point, second point. Here's the third point. And then the fourth point, same idea. 1/3 x is equal to 4. So now my new x value has to be what? X coordinate has to be 12 after stretching it by a factor of a third. And then add 1 unit to the y coordinates. So the whole graph gonna shift up 1 unit. So it'll be 12, 3 is my final answer. So this is a new, right? Stretching it by a third factor and then shift up 1 unit. So this is my part D. So this is a vertical shifting and a horizontal stretching together in this part. If you are reviewing on this, my recommendation is do the stretching and shrinking first, then reflections, and last will be shifting up and down and left and right in that order, okay? To make less mistake. Now, let's move on to the next example, which is the trigonometric functions. Graphing cosine 1/2 x. We know that the range of the cosine is between 1 and -1. Cosine is a 2 pi period function. So I want you to see how this graph is being transformed. So I'm going to show to you the very first parents graph first. Okay? So that's being said that here's 1, here's -1. That's my range. And I'm going to make it every 2 units. Cosine of 0 is 1, and cosine of pi over 2, right? Let me do this. Cosine of pi over 2 is 0. Cosine of pi is -1, and then so on and so forth. Right? 3 pi over 2, and then 2 pi, 3 pi, 4 pi, so on and so forth. So for cosine, the graph will be like this. For 2 pi period, because pi over 3 will be 0 again right here, right? It crosses. So that's cosine graph. Now, what we want is what? We want horizontal stretching. And notice that is 1/2 times with what? The input value. So everything's going to be stretched by a 1/2 factor. In our trigonometric, from our trigonometric, graphing techniques, we learned this. Cosine is 2 pi period divided by b, which is the coefficients in front of the input value. That is our period. So in this case, 2 pi divided by 1/2, that will become 4 pi. Okay. 2 pi divided by 1/2, that is become 4 pi. So that means our period is 4 pi period. And what happened is our points for the cosine is also stretching horizontally. See, notice that this is a parent graph, the one that I drew in black, dotted. So now I have at 0 will be 1, that point doesn't change. Because as you stretch it by a factor of 1/2, right, then it's 4 pi period now. So I have my 5 easy point, which is going to be pi will be 0, 2 pi will be -1, 3 pi will be 0, and then 4 pi will be 1 again. So this will be how it's going to look like after stretching horizontally from the parents graph that I drew on dotted part. Okay. So you still can use the transformations technique that we talked about in a previous example, but trigonometry function has a different way of graphing it, which is finding out the period first and then make it 5 good points. That's how I taught in my trig class, and that's what I'm expecting you need from you also. You need to know how to give me the 5 good points and get the shape out of it. Okay, and the 5 good points are basically easy. Once you find out the periods, then your period will be the beginning of the periods to the end of the periods. And then you just basically find out the midpoint. That'll give you 5 good points right there. In this case, it's easy enough just to count it, right? 4 pi periods, 4 equal parts will be pi period each. So review on the trigonometry. Okay. Next example is y equal to 1 minus cosine x. If you are okay with this, that's fine. If if you want to be more clear, try to rewrite it in this format. Negative cosine x plus 1. So that will help you to see that there is a reflections and there is what? A vertical shifting, right? Because cosine is a parent's graph, which is like a y value. So in this case, it will be vertically, shifting upward 1 unit, and then we have what? Reflecting about the x-axis. So continuing this, I'm gonna say that here's 1, 2, -1, -2, and I'm gonna make it this time 1, 2, 3, 4, because I don't need to stretch anything. So this will be 2 pi and then pi. So my increment is pi over 2 on every 2 units. I want to see a nice, neat labeling and a scaling. That's what I expect, the least I can expect from you, right? At this level. My parent's graph, let's try to take a look at our parent's graph. The parent graph, the cosine of 0 is 0, 1. Cosine of pi over 2 is 0, and then cosine of pi is -1. 3 pi over 2 is 0, and then 2 pi is 1. So I have a cosine graph like this, the parent's graph, so that you can see how it's going to change. Right? On the test, don't really need to give me this parent's graph. Right? You can draw the final graph right away. And be careful with using calculator, because I will ask for a specific 5 good points to see it. You need to label and then tell me what are those 5 good points are after you do the transformations as well. So in this case, when I do the transformations, remember stretching, shrinking, reflecting first. So I'm going to do the reflecting first and then shifting. So in this case, reflecting about the x-axis. So this point, the very first point on the left, when you reflect about the x-axis, that will become a -1. And then you shift up 1 unit, so it will become, here is my point. 0, when you reflect about the x-axis, still going to be 0, right? My y value on the second point. But when you shift up 1 unit, it will be at 1. And this third point is pi -1. When you reflect about the x-axis, this -1 become +1, which is right here. And then shift up 1 unit, so it will become what? At 2. Okay. Now, the third point is the same thing. The fourth point is the same thing as the second point, right? Because when you my original y value on the parent's graph is 0. When you shift, when you reflect about the x-axis, my y coordinate is still the same, 0, and then shift up 1 unit, so it will become at 1. For the last point, that is 2 pi comma 1. When you reflect about the x-axis, this y value, instead of 1, it becomes -1. And then you shift up 1 unit, so it will become at 0. So finally, I got my transformations, reflect and then shift up 1 unit. Of the cosine graph, something look like this. If you know how to draw cosine, sine, tangent, then secant, cosecant, and then tangent will be the same, right? Except what? It's gonna flip it open. The next topic that we want to talk about is algebra of the functions and the compositions of functions. Composition of functions is very important for one of the sessions that we're going to learn later on, which is called the chain rule, right? Taking derivative by chain rule. It's very important that you need to know how to look at your composition function. But let's start with this algebra of the function first. Addition of the functions. Here's a notation that's not new to us. Subtractions, multiplications, and divisions. And you can extend it, addition, subtractions, multiplication by adding what? plus h, so on and so forth. And what I want to recall is a domain. Domains of addition, subtractions, and multiplication of two functions is simply the intersections of the domains of those two functions. Right? But however, in the divisions, the quotients, it's not only that you need to consider, right, the domains of intersections of domains of f and g, but also you need to exclude any x value which gonna make the denominator functions go to 0, because of this is irrational, right? That's a old concept that we have. So you are excluding, right, from this intersection, you are excluding any x value that's going to make g of x equal to 0. So let's take a look at on the first example. It's given to you that f of x is square root of 5 minus x, g of x is square root of x minus 3, and we want to find out additions and then divisions and then their domain. Since we need, right, the domain of f and g before we can talk about the algebra of domain of functions, we want to find out on a side work, we want to find out the domain of f and a domain of g so that we can work on it. Smoothly. Function f is a radical functions, so the domains is radicand must be greater than or equal to 0. So in this case, our radicand is 5 minus x. So therefore, 5 is greater than or equal to x. So our domain is the value of x is less than or equal to 5. Now, the next one is g functions. Once again, g functions is also a radical functions. So domain is any x value which is going to satisfy this inequality, which is radicand is greater than or equal to 0. So in this case, my radicand is x minus 3. So therefore, my domain is x is greater than 3, greater than or equal to 3. Now that I know the domains of each functions, then I can answer all of them at once for each questions. Part 1, f function plus g functions of x. This simply say that the f functions evaluating the input x, adding with g functions evaluating at the same input. Another way of saying this, we are adding two function values together on a particular input. And this basically look like square root of 5 minus x plus square root of x minus 3. We cannot simplify any further, so that's our final answer. The next step is to find out the domain of this f plus g. That is simply saying that the intersections of those both functions, domain of both functions. And you can see that domain of f is less than or equal to 5. Domain of g is greater than or equal to 3. So to visualize it on a real number line, here's 0, here's 3, here's 5. For domain for f is anything that's less than 5. Domain for g is anything that is greater than 3. So therefore, you can see that intersection is only between 3 and 5. So therefore, domain for this g plus f plus g is from 3 to 5. Any value that is outside of it, it will not work for this function. For example, if I pick 6 and substitute it into the functions, right? 5 minus 6, that's giving a negative number, which is a complex number already. So it's not working. Next, part B of this is f function divided by g functions of x. This is simply saying f of x divided by g of x. When I write it down in algebraic formats, that will become square root of 5 minus x divided by square root of x minus 3. You can rationalize the denominator, but not necessarily at this point. So when we are trying to find out the domain of f divided by g, right, this quotient, similarly, we need to talk about the intersections of 2, which is between 3 and 5. But however, one extra thing that we need to consider is the denominator. Any x value that's going to make the denominator functions equal to 0, we need to exclude it. In this case, the denominator portion, if you look at it, x cannot be 3. So therefore, we are basically talking about not including 3. And that is the difference between part A and part B on this problem. So you need to be extra careful with what algebraic functions that we are talking about. And then consider appropriate domain. Moving away from this part, we are looking at the composition functions. The composition functions is f composed g of x is written by f of g, right? F not dot is like an open circle, g of x. This simply say that the g functions will be the input of f functions, which is f of x, the input is g of x. So therefore, the domain of this composition function is any x value which satisfy the g function, which is the domain, such that this g of x, the value, is a domain of f functions. Okay? Because the composition function is like, two machines stack it up together idea. So you have the inputs x into g functions. So the outcome is g of x. But however, you're using this outcome to put it into another machines, which is f. So that will give me f of g of x. Right? Like this kind of idea. So therefore, first you need to find out what all the x value that satisfy what the g functions. Not only that, you need to also consider the range of the g functions must be the domain of f. Right? Anything that does not work, you need to exclude it since in the beginning, which is on this x. So I have f functions and then g of x. So we want to find out the composition functions, the domain of it. So I want to look at this for domain of f, right? Domain of f. Since f is a polynomial, domain is all real number. And I want to think about the range of f also. Now, this you have to be careful. I can quickly see that, okay, from the transformations of graph on this simple functions. X squared is parabola opening upwards. So the range is from 0 to positive infinity. But because of shifting up 3 units, so now the range is from 3 to positive infinity. It's 3 is included. So that's how I quickly can get on the basic function like this. Right? Now, domain of G that is from what? 0 to positive infinity. So if I talk about f composed G of x, this is simply saying f functions, the input is G functions. So f functions, the input is G function, that is square root of x. And where are we substituting the square root of x? We are substituting the square root of x into x squared plus 3, which is the f functions. And when I simplify that, this will become x plus 3. Notice that if I just look at this, okay, if I just look at this, then it's all real number. The domain is all real number. But that's not always the case. That's not always true. So you need to go back and double check on according to the definitions. So we are talking about the domain is all the x value. That is the domain of G functions, such that G of x is a domain of f functions. Right? So first of all, in this case, my G of x is the square root of x. So G of x is basically what? The range. Will this, any value in this range will cover in the domain of G? That's what we need to look at. Right? In the domain of. So let's take a look at on this. My domain of G is from 0 to positive infinity because it's square root. My domain, my range of G, right, is also 0 to positive infinity. So notice that this range is basically part of the domain of f, because domain of f is what? Every number between negative infinity to positive infinity, which include every value in the range of G. So therefore, what that tells us is what? Domain of G is also a domain of what? F. Okay? So that tells us the domain of this composition functions is from 0 to positive infinity. See, like I pointed out earlier, if you just look at this final answer and then talk about the domain of this composition function is negative infinity to positive infinity, then you will be getting the wrong answers already. Because the G functions does not work from negative infinity to positive infinity. So if you don't have an output value in the G functions, you can't even have the input value of f, and you cannot continue. That's the whole point of it. So it's very important that you need to check it very clearly and then carefully. Okay. Continue from here, and we want to find out the f composed of G, G composed of f. So the first part, f composed of G of x. Write down step by step. I will recommend, so if you're recalling. So this will be f of x input is G of x. In this case, G of x is square root of x. So therefore, input minus 1, my input in this case is square root of x. Cannot simplify any further, so therefore that will be square root of x minus 1. For the second part is G composed f of x. that is g functions, the input is f functions. This time my f functions, the input, the f function is x minus 1. And we are inputting this into g functions, which is square root of the input, that is x minus 1. So my final answer in this case is square root of x minus 1. So at least a minimum, I want to see this step on a test, the equivalent form notations. What are you substituting, right? And then give me the final answer after you substitute it. And if you need to simplify, you take most step. Okay? So not necessarily f composed of g and then g composed of f are the same. Okay. Sometimes it could be, sometimes it's not. It could be only if they are inverse of each other. And the next example is showing you the extensions of this composition functions, which is composing 3 functions. Right? We want to find f compose g compose h of x. So that's basically showing to you that the f functions, let me copy down the question first. The f functions, the inside the f function is g functions. Inside the g function is h function. So functions within the functions. So always, like, the last functions input it into the second to the last and then continue. So what we want to do is we want to look at step by step and then making sure that it comes out nice and neatly. So f functions. Inside the g functions, we're going to be substituting with the formulas of h function, which the formula in this case is 2x plus 1. And this 2x plus 1 will be evaluated in the g functions. So therefore, we're going to be looking at f functions. The input of f functions, we're going to be g of x minus 2. So I can take a look at on the side work to make it nice and neat and clear. G of 2x plus 1. My g function in this case is what? X to the 5th power. So it'll be 2x plus 1 to the 5th power. So this entire notation, g of x plus 2, right? Remember this is my side work, because you don't want to do a lot of things in this little brackets and then, simplifying and stuff. So now I will get what? 2x plus 1 quantity to the 5th power. That's what g of 2x plus 1 representing. And finally, I'm going to substitute, right, this entire part into the f functions, which the f function is the input over input plus 1. So in this case, my input will be that 2x plus 1 to the 5th power. 2x plus 1 to the 5th power. Okay. So that will be my final answer, because I don't want to multiply this out 5 times. Right? And then we cannot reduce at all. So this would be my final answer. Composing function, you can do it systematically one by one. But one more important thing is, if you have a composite functions, you need to know how to decompose it into 2 fractions, 2 functions or 3 functions, composition of 2 functions or 3 functions. And that's the important part that we need to be able to see it very quickly to do better on one of the sessions later in chapter 2. So, being said that, the next example that we want to look at is this. Given to you f of x, which is tangent to the 5th power sine of x. We want to find the functions f, g, h such that this uppercase f function is the compositions of f of g of h. So what we need to do is we need to look at this way. The most outer function is f functions. The next inner function is g functions. And the most inner functions is h functions. So you need to be able to see which is the most outer function, what is the next next inner function, and next inner function, so on and so forth, in that order. So f of x is tangent to the fifth power of sine x. Another way of saying this, a lot of times we tend to make a mistake right here. You need to be careful with that. Tangent to the fifth power, you have to look at this way. That is tangent of the argument to the fifth power. You need to be able to see this so that you can see the most outer function in this case is the power function. The next inner function is the tangent function. And only the last, the argument of the tangent is another function, which is the most inner function, this one. So therefore, when you write it down, the decomposing into three functions, the most inner function is sine of x. I can see that already. The next one is tangent x. And the most outer function is fifth power. So I can say that x to the fifth power. That way, when you do the composition function, this sine of x will go into this right here. And then this entire expression will go into what? Fifth power part. So that's the part that you need to be able to break it down very quickly. The most outer, the next inner, and the most inner, and so on and so forth. So what I want you to do is pause for a second and then try to do the next a few examples, right? The next two examples, and we're gonna try to check. Okay. Example, f of x is equal to 3x over square root of 3x minus 1. And we want to write this function as a composition of f and g. So what is my outer functions f of x and what is my inner function g of x? From here, I can see that 3x and then 3x is another functions. So I can take a look at it as here, input over square root of input minus 1, and my input is 3x. So therefore, the outer function is x over square root of x minus 1. The inner functions, the function that's going to input is 3x. And the next example, f of x is square root of sine of x plus 2. And we want to write this uppercase f function as f of x, g of x, h of x, which is the f composed g composed h. So in this case, the most outer functions, what I see is square root of input. And the next is what inside this input, I have sine of input. And the last input is x plus 2. So therefore, the most outer function will be square root of x. The next inner is sine of x. And the last one is x plus 2. And that is decompositions of these functions. And it's very important that you need to be able to see that very quickly and correctly on which is the most outer function, the next inner, and the most inner in that order. And this is the end of 1.3. And don't forget, the homework is in the beginning of this sessions, which is right here.